Okay, so follow along with me here, guys. Oh, I don't have the answers for this one. I should have checked that earlier, I guess. Eh? All right, that's no problem. We'll be able to figure it out quickly. All right, so what's the final velocity of a boat that is accelerating okay, from rest, okay, for 13.4 seconds at 4.5 meters per second squared. All right, so they're asking us for VF. We don't know what that is, okay? We're accelerating from rest, so VI is 0 meters per second, okay, and we're doing that for 13.4 seconds at a rate of 4.5 meters per second squared. 1 mark for that, okay? That's their givens. Okay, equals A equals VF minus VI over T. Okay, 1 mark for that formula. We got to manipulate for VF. So we're going to multiply both sides by T. Okay, so it comes over here and then add VI. So we will have VI plus T times A, okay, equals VF. When we plug in our numbers, that's going to be 0 plus 13.4 times 4.5. 13.4 times 4.5. All right, gives us 60.3 meters per second. All right, so mark for the manipulation, mark for plugging in the numbers, mark for the final answer. Why did I not put a vector on that? Yeah, it says final velocity though, but it never gave me any directions. Okay, so if you put positive on it, that would be fine. It is positive. All the numbers in the question were positive, even though it wasn't indicated that. Okay, but truly I should have done a better job of writing that question and put positives on everything. Okay, really what we did there was find speed. Okay, not necessarily velocity on that one. Okay, questions on that one? All right, so it's out of 5. And then our second question. Okay. Okay, so we have an object that reaches a speed of 29 meters per second. So is that the initial or final? Final. Okay, after accelerating at 7 meters per second squared for 2.9 seconds. How fast was it going initially? Okay, so we're looking for its initial speed. This time it says speed. Okay, so do I really care about directions too much here? Other than acceleration, which would be important to know, but it's positive. It doesn't outright say negative. So, all right, so 1 mark for givens. Okay, 1 mark for the formula. Okay, then we got to manipulate for VI. And we said this was kind of the tricky one. Okay, when we do that, we're going to multiply both sides by T, add VI to both sides, and then do what with T times A? Minus it over to the other side. All right, so we're going to end up with this. VI equals VF minus T times A. All right, so mark for that manipulation, and then we have 29 meters per second minus the 7 times 2.9. All right, so on our calculator, that's going to be 29 minus 7 times 2.9. Okay, so we've got 8.7 meters per second as our initial speed. All right, so mark for plugging in numbers, mark for the final answer. It's out of 5, whole thing's out of 10. Let them see it, put it in the box. All right, so at the end of the day, I had gone over this example, okay? The importance of going the speed limit in a playground or school zone, okay? Because we saw that speed has a, what kind of relationship with energy? Exponential, okay? If I double my speed, I'm going to have 4 times as much kinetic energy, in which case it's going to take 4 times as long for me to stop distance-wise. So it's an important thing for us to realize on that. Okay? Now, the whole reason that came up was because we were talking about kinetic energy, but we were also talking about change in energy being equal to what? Work. Okay? And work is force times distance. So this was really the first time that we had combined the two formulas. Okay, we had combined the formula for work, force times distance, with one of our energy formulas. Okay, in this case, it was kinetic energy. Okay, kinetic energy final minus kinetic energy initial. It's just our kinetic energy final was what? Was 0 because we would come to a stop. Okay. All right. Is that ringing a bell for everybody? Yes. No. Okay. All right. So then we talked briefly about that, and I think we got to this, right? Did we do this one? Okay, so we got through that one. All right. Right. Then I want you guys to try this one. Okay? I'll give you a few minutes on this one, and then we'll go over it together. Okay. So a tractor's pushing a rock. We're given the mass, and it's doing that from rest to a speed of 4 meters per second over a distance of 25 meters. What force is exerted? Okay. So the rock is changing its speed. Agreed? What kind of energy is changing then? Kinetic. All right. So we know there's a change in kinetic energy going on. And the only way that a change in kinetic energy goes on is if what's being done? Work. Okay. So right now then, we know that work is causing a change in the kinetic energy of the rock. Everybody okay with that? Yeah? All right. Do I have a formula that calculates work? Okay. How do I calculate kinetic energy? Half mv squared. Okay. And if I'm calculating the change in kinetic energy, that means 1/2 mvf squared, the final kinetic energy, minus 1/2 mvi squared, the initial kinetic energy. Everyone with me there? Okay. What's vi? 0. So what's 1/2 mvi squared? 0, because multiplying anything by 0 makes it 0. Okay, so if that's 0, there's no sense leaving it there. Do I have all the information except F? Okay, I have D. They told me it's 25 meters. They told me the mass was 550 kilograms, and they told me the final speed was 4 meters per second. So can I manipulate to find the force being used? What do I do? Divide by D, right. All right, so now I've got my formula that'll calculate force for me. I just have to plug in my numbers. So I'll have 1/2 times 550 times 4 squared divided by 25 meters. Okay, so does everyone follow what we did there? Okay, whenever you're looking at a question where it's asking about force, it's probably a work energy theorem question, right? Because that's the only situation, at least in Science 10, where we're going to deal with force. Okay, the other reason we know this is a work energy theorem question is that what's changing in this question? Kinetic energy. That's the trick. Being able to read a question and identify, is energy changing? And if so, what kind? Okay? So that was the first thing I did. Is when I was reading through the question, I saw that the speed of the object had changed. That meant to me I've got to have a change in kinetic energy going on. And if there's kinetic energy that's changing, work is being done. So I set work equal to the change in kinetic energy, because that's the work energy theorem after all. Okay? All right, so when we plug in our numbers, right, we're going to have 0.5 times 550 times 4 squared, okay, divided by 25. All right, so we're going to be using 176 newtons of force. That is a child's remote control electronic tractor, because 176 newtons is like a tiny, puny force. Why is it so small? This was supposed to be a tractor moving a 550 kilogram rock. What makes moving a rock so difficult? Friction. Did we say there was any friction in this question? No. Moving a 550 kilogram rock on a frictionless surface is really easy. Walking on it would be hard, but moving a rock on a frictionless surface is really easy. Okay, because there's no friction, and that makes everything difficult. So yeah, it's a bit of a simplified question. That's why we get a weirdly small number. Okay, and we got to remember also, units for force are newtons, N. All right, what if I get a question where instead of having a change in speed, it says that the object is lifted from one height to another. Jared? It would be a change in potential energy. Would I still set FD, work, equal then to energy? Would I still set those two equal? Okay, I would. It's just now instead of using 1/2 mv squared, I'm going to use mgh, the formula for potential energy. Okay, don't worry if you don't get it right now. We're going to work on it. It takes a little while to get the hang of it. All right, so a mail carrier picks up a 10-kilogram package on the 3rd floor of a building where they are 30 meters above the ground. And they deliver it to the 10th floor that is 100 meters above the ground. Okay, how much work is done? All right, is there any mention of a change in speed in this question? Okay, what kind of energy is changing in this question? Potential energy. Do they ask me to calculate either force or distance? Do they give me either one of those? Not really. What are they asking me to calculate here? Work. Okay, is work a change in energy? Can I figure out how much the potential energy of this package changes? Okay. Does it have potential energy when it's 30 meters above the ground? Does it have more potential energy when it's 100 meters above the ground? Can I calculate how much it has at each point? Yeah? Okay. So, let's look at it this way. All right? Work is a change in energy. In this case, it's a change in potential energy. Okay? This is what I'm being asked to find, so I don't have to put FD in here because it's not asking me for either one of those, just ask me for the work. All right, so this is going to mean the final potential energy minus the initial potential energy. All right, formula for potential energy is M times G times H. Final minus M times G times H initial. Well, it's being moved, but its speed isn't changing. It doesn't take any work to move something without changing its kinetic energy. Okay? So if I lift something, I'm only working against gravity. It would take extra work if I wanted to accelerate it against gravity. I'd have to push harder, right? But in this case, since I'm only moving the package and I'm not changing its speed, I'm doing it at a constant speed to there, I haven't changed how fast it's going. Follow me on that? Okay. All right, so we've got, what was the mass of this thing? 10? Okay, so we got 10 kilograms times 9.81 times 100 minus 10 kilograms times 9.81 times 30 meters. All right, so all right, so how much work is done? 6,867 joules worth of work. Okay, I mean, would you get tired if you were carrying a 10-kilogram box 70 meters up a building? I would think so. Okay, that would take a lot of energy. That'd be a good way to burn calories. Okay, that's a lot of stairs, 70 meters. That's a very tall building. That's like the new Bow Tower in downtown Calgary. Pretty tall. Is that making a little more sense? All right. So basically, guys, when you read a question, you have to visualize what's going on, and you have to see what kind of energy is changing. Fortunately, in Science 10, we're never going to have a question where both kinds of energy are changing. All right. So you're just going to have to identify one or the other. When you get to Physics 20, then you'll have both. Mathematically, they're a little more difficult, but not really. The nice thing about them is you know that, well, most of the time both kinds of energy are changing. I got to plug them all in. Okay? In Science 10, you got to pick one or the other. Okay. Try this one. All right. So we said that the bulldozer has kinetic energy at the beginning of this question. Agreed? because it tells us it's moving at 2 meters per second. Let's calculate how much energy it has at the beginning. Okay, so we're going to calculate its initial kinetic energy. We're going to do that right now because we have a formula for that. 1/2 mvi squared. All right, so that's going to be 1/2 times 2,500, okay, times 2 squared. Okay, so all right, so we got 5,000 joules. Okay, so sorry, this is the truck. The bulldozer's pushing the truck, but the question's about the truck. Okay, so the truck has 5,000 joules worth of energy at the beginning, and then the bulldozer does work on it. Agreed? So does the truck have more energy or less energy at the end of the question? More. Okay, it's having energy put in, right? Work is an input of energy in terms of the truck. Okay, so if I'm trying to figure out how much energy the truck has at the end, can I do this? Can I say that work is the final energy of the truck minus the initial energy of the truck? Okay, right? We've done that before, right? We've basically set up every question like that. Work's a change in energy. Okay, so I want to find this number. So what do I do with this number? I add it to both sides. I mean, that makes sense, right? We said it's going to have more energy at the end of the question than it had at the beginning. Okay, because this work that the bulldozer does adds on to the energy the truck had at the beginning. All right, so we have, was it 7,500? 7,500 joules worth of work, okay, plus the 5,000 joules worth of work we had at the beginning, okay? All right, so we're going to have 12,500 joules, right? All right, so our final energy is 12,500 joules. So is the truck going faster now? Yes, it is. Okay, so if that's my final energy, does that number equal this? I had some energy, I did some work, now I have more kinetic energy. So now, if I solve for V, is it going to be a bigger number? What do you think? I have more energy. Should V be bigger? Okay, so that's what I'm going to do. I'm going to solve for V. Okay, so I'm going to divide both sides by half of M. And then I'm going to do what? I'm looking for V, and V is squared, so I have to square root. Okay? All right, so I'm going to have the square root of 12,500 over half of, keep forgetting what the mass was, 2,500. Okay, so I should probably use brackets. That would be better. 12,500 divided by 0.5 times 2,500. 3.16 meters per second. Okay, now I've broken that down really piecemeal. I wouldn't do it that way myself. Okay, I'm going to show you how I would do it. It's mathematically the same, but not broken down in the same way. Okay, what I would have done here is kind of skip some of these breakdown steps. I would have initially said this. Now, I said that before, right? When I said work is EF minus EI, that's what I said. Okay, but I'm plugging in everything right at the beginning here. I'm going to say that work equals 1/2 MVF squared minus 1/2 MVI squared. Okay, I'm bringing this over to this side, so I'm going work, not equals, work plus 1/2 MVI squared equals 1/2 MVF squared. And then I'm dividing half of M. Does half of M cancel when I do that? No, it doesn't. Okay, I've got an addition subtraction operation on the top. I can't cancel a division from the bottom. All right, is that what we did? Same thing? I just didn't break it down quite as much. I broke it down that way just to explain kind of the process. Okay, if I was doing it mathematically, I'd have done it this way because it's a lot less steps. Okay, everyone following me here? Okay, the big thing is we have done work as a change in energy each and every time, haven't we? Okay, what we've had to do is figure out what kind of energy it is and then solve for some part of that. Okay, that's the way they all work. Okay, they all set up essentially the same way. Okay, either you have to figure out force, you got to figure out distance, or you got to figure out work. Okay, by subtracting the two energies, something along those lines. Okay, you should probably write these down. They're not in your notes, but they're steps. Okay, for solving work energy theorem problems. Okay, we always start out with that step. Write out the givens. Okay, when you do that, you'll figure out whether you need to do force times distance or whether they already did it for you by giving you work in joules. Once we've written out our givens and we've read the question, reading the question is important. I mean, I know that step's not on here, but I kind of take for granted that you wouldn't do anything until you'd actually read the question. Okay, from the context of the question, can we figure out whether it's potential energy that's changing or kinetic energy that's changing? Once we've identified the type of energy that's being changed, that's when we set this up. And this is the step you guys saw me do every single time so far, right? I said work's a change in energy, and then I expanded that to force times distance equals the final energy minus the initial energy. And that could mean either it's kinetic, so I'm going 1/2 mvf squared minus 1/2 mvi squared, or it's potential, and it's mghf minus 1/2, or sorry, minus mghi. Okay, we set it up that way. Then you manipulate for whatever it was you were asked to solve for. So again, it comes down to being able to understand the question. Okay, when you read the question, it becomes a reading comprehension thing. When I read the question, was there a change in height or was there a change in speed? Okay, what does that mean for me? Well, if it's a change in height, it means potential energy is changing. If it's a change in speed, it means kinetic energy is changing. All right, questions on that? Does anyone still need that? Okay. Okay, so I want you guys to try this one here. Calculate the force involved in lifting a 50 kilogram mass to a height of 1.5 meters. That question implies it started where? Well, yes, also from rest, but it never really changes its speed so much. It's changing its height from zero, right? We have to assume, since it doesn't say otherwise, it says to a height of 1.5 meters. Well, that's usually measured from the ground. Height's usually measured from ground level, which has a height of 0. Okay? Okay, if I'm lifting this thing, what kind of energy am I changing? Potential energy. All right, am I doing work? Yes, I have to be doing work because I'm changing energy. All right, do they give me force and distance? Okay, they don't give me the force, no, but they tell me the distance because the distance is the same as the height. That's the trick on this question. Okay, the distance and the height are the same number. All right, so I've got that work is a change in potential energy. So force times distance equals m times g times h final minus m times g times h initial, which we already know is 0. All right, can I solve for force? By dividing by d. Okay, so really, since h and d are the same number, what do they do to each other? All I got to do is multiply m times g, which makes sense Because yesterday we talked about how that's the force of gravity. Is that the force you do work against when you lift something? It is. Okay? If I want to lift something and I don't want to change its speed, all I have to do is apply exactly the same amount of force as what gravity is pulling down with. If I want to accelerate, then I got to exert more force. Okay? But if I just want to move it upwards without changing its kinetic energy, I got to exert a force equal to that of gravity. Okay? Same for lowering, in fact. Okay. These should be on there. The energy formulas. They're down here. Kinetic and gravitational, right near the bottom. Well, I mean, you can put that. You can put the final minus initial on there, but you're not going to get that on a test. Okay, that's because that's work energy theorem. That's something. It's actually it's on there too, right? It says that work is a change in energy right here. Yeah. Okay. Um, right. Try that one. We talked about this one yesterday. We talked about ramps and we talked about hills and ramps yesterday. Okay. When you push something up a ramp, you're changing its what kind of energy? Only its potential, because it never says here we're speeding it up. It just says we're moving it to the top of the ramp. Okay. Okay. So yesterday, when we looked at this example, we said that it doesn't matter whether you push it up the hill or lift it to the top, you do the same amount of what? Work. Because in the end, it arrives at the same place, the top of the hill. And at that point, regardless of how it gets there, it has the same amount of potential energy. All right, so that's what we have to keep in mind when we're solving this. Okay, the work that this person does in pushing the block up the ramp this way is the same as if it was lifted this way. Well, if I lifted it, I'd have a direct comparison for the change in potential energy from 0 to here. Agreed? But since I don't have this number or any numbers to do with this, I have to go with the longer way, which was using 150 newtons of force to push it 25 meters up the ramp. Okay, so in doing that, I've done this work. Agreed? And they gave me force and distance. All right. So force times distance is going to equal the change in potential energy I achieve by pushing it up the ramp. How do I calculate potential energy? M times G times H. All right, so M times G times H final minus, how much did I have at the beginning? 0. Okay, do I need to bother writing that? No. All right, here's my setup then. The work I do pushing it up the ramp is equal to the final potential energy of the block at the top of the ramp. Do I have the mass of the block? And do I know what G is? All right, so not too hard to calculate HF then. All right, so all I have to do then is use my 150 newtons times 25 meters, the length of the ramp, divided by, what was the mass of this thing? 35 kilograms times 9.81. Okay, so that should come out to 10.9 meters when we do that. Okay, that's about as difficult as they would get. Okay, and really, mathematically, there wasn't much to do there, was there? Okay, but the difficulty lies in interpreting the question and understanding that work energy theorem and how it works. Okay, that's the difficulty here. The math is not the difficult part of these questions. Okay, I think I have maybe one more or not. Yeah, I do. Okay, there's one more here. Okay, try this one, trying to figure out how fast the baseball is moving. Okay, after this pitcher throws it. All right, if you throw a ball, what kind of energy are you changing about the ball? You're changing its kinetic energy. All right, and I mean, if you've ever watched like slow-mo of a pitcher pitching a ball, or or seen a picture of them kind of wait like right when they're first starting, their arms rotate like so that I can't even do it. My arm will just come off. Okay, their hand is like down here, right, when they're pitching that ball, because that increases the distance over which they exert that force. They've got that extra flexibility for a while till their rotator cuff goes, and then they don't have that anymore. That's a very common injury for pitchers because the rotator cuff is the muscle that allows this part of your arm to rotate, and the more flexible it is, the farther back you go, and then the greater the distance over which you can exert your force on the ball, and then the faster you can throw the ball. Okay, all right. So we're throwing this ball that has a mass of 0.250 kilograms, exerting 300 newtons of force on it over a 2.2 meter path. Okay, we're going to assume that the ball starts at what speed? 0, so it has no initial kinetic energy. All right, we're trying to figure out how fast it's going to leave his hand at. This is really fast, by the way. Really, really fast. All right. I mean, if you've ever seen how quickly a major league pitcher can throw a ball, I don't know how anybody hits those things. Okay, like basically the batter's got to decide if he's going to swing or not before the ball leaves the pitcher's hand. Okay, like it comes that fast. I don't know how they do it. I wouldn't even want to stand there. Okay, all right. So I know the force. They told me that it's 300 newtons. Okay, they told me the distance over which it's going to act, 2.2 meters. I know that the initial velocity is 0 meters per second, or initial speed is 0 meters per second, which means the initial kinetic energy is 0. Okay, and they told me the mass of the ball is 0.250 kilograms. All right, I'm changing the energy here, or the pitcher is changing the energy because they're doing work. Okay, work is force times distance, and that's going to equal 1/2 mvf squared minus 1/2 mvi squared, which we already said was 0. What am I looking for? Vf. So what do I do with 1/2 an m? Divide it. And then what do I have to do? Square root it. Okay. So we will have our 300 times 2.2 over 1/2 times 0.250. All right, and that'll give us our 72.7 meters per second. Okay, everybody all right with that one? All right, so that would be as tricky as a kinetic energy one would get. Okay, so you saw as tricky as a potential energy one would get on the previous question. This is as tricky as a kinetic energy question would get. They're all essentially the same. Okay, nothing's changing. Don't pack up yet, guys. There's still 5 minutes left in class. Okay, I don't want to see anyone packing up yet.